So good evening everybody, and thank you for the invitation to come and talk to Knutsford SciBar. So this is the beginning of everything. As you can see from the subtitle, a brief description of the origin and the very early history of the universe. Let's have a quick look at a sky survey. So this might look like an artificial animation, but really it's a three-dimensional atlas. It looks like it might be a simulation, but in fact the positions of galaxies and the distances to various galaxies have been measured, and this is a three-dimensional rendition of our neighbourhood of the universe. And it's a sort of fly-through, but treat it more as a 3D atlas rather than a simulation. So when we look at the structure that's out there, we see lots of galaxies, but we notice that the galaxies aren't uniformly spread. They seem to be clustered, and there seems to be particular lines or filaments where galaxies and clusters of galaxies seem to lie. And there are some regions which seem to be rather sparse, so-called voids, where there seem to be very few galaxies. So if we want to understand where the universe came from, we have to be able to explain why it looks like this now. Yes, the universe was born 13.8 billion years ago, but if our understanding of that particular event is correct, and if our understanding of the laws of physics that govern how the universe has evolved are correct, then we should get to this point, 13.8 billion years later, and be able to explain why the universe looks the way it does. So with the Hubble Deep Field or similar images, we see a great number of galaxies, perhaps many thousands in the Hubble Deep Field, which of course just covers a tiny patch of sky. So we have a few sample galaxies to look at, but still we have a job to do to try and understand where it all came from. There's an awful lot out there: galaxies, stars. We know galaxies aren't made just of stars. We know there's a whole load of gas and dust in there as well. But we can ask, where did all that matter come from? So what I'm talking about is the creation of the universe. When did it happen? It happened 13.8 billion years ago. We know that number fairly accurately. How long did it take to make a universe? It took about 3 minutes, and you'll see why 3 minutes is relevant in due course. Where did it happen? Some people seem to think that if we look out into the cosmos, we will find the point at which the Big Bang occurred. No, it doesn't work like that. The universe was made in a Big Bang and then expanded, so in a sense, the Big Bang happened everywhere. Why did it evolve the way it did? Well, because of the laws of physics. And how do we know all this? Because of the laws of physics. You can tell that I'm a physicist, and I believe that the laws of physics basically answer everything. In this case, that gets us an awful long way. Let's just have a few general comments before we get stuck into it. Nature is not repetitive. In other words, the same thing doesn't happen over and over and over and over again. It may seem that way during the last year of lockdown, but nature does not absolutely repeat. In other words, if nature simply did the same thing over and over again, it would be very boring. And nature, at the opposite end of the spectrum, is not unpredictable. In other words, if it was totally unpredictable as to what's going to happen tomorrow, is the sun going to rise? Well, how do we know? It might not. If nature was completely unpredictable, it would be impossible to make any sense of the world whatsoever. So nature doesn't simply repeat itself, and nature is not so unpredictable that we can't make some sense. Nature is somewhere in the middle. In other words, nature is interesting. So we can ask ourselves, how does the universe work? How does the world work? And the world in the most general sense, not just planet Earth, but the world around us. We can ask it in terms of, what are the rules of the game? In other words, if we look at this particular scenario here, we can ask ourselves, how did this particular situation come to be? What are the rules of the game that would produce this particular result for these little shiny pieces moving around on this 8x8 square grid here? If we had no understanding of what the game of chess was, could we work out the rules of chess by looking at this photograph? And the answer, I guess, is no. You might be able to figure out that some pieces are coloured differently to other pieces, so maybe two players are involved with this particular game. But you can't look at this and deduce what the horse does versus what the queen does versus what the bishop does versus what the rook does. Why are there lots of these little ones that we call pawns? You can't figure that out just from a picture. And by the same analogy, you can't just look at a galaxy and say, okay, that's a galaxy, it seems to be full of stars. We can't work out why it looks like that and where it came from just from that one snapshot. No more than we could with a game of chess. But what we could do with a game of chess is to say, well, let's not look at a single image, let's watch a video of somebody playing chess, and then we'll see how the pieces move. And if we watch a game being played, we'll have a much better idea of what each piece is allowed to do, and perhaps we can figure out what the end game is, what's the point of this particular game. What we can't really do is to do the same with galaxies. We can't sit and watch that galaxy and see what happens over 13 billion years to get an idea of where it came from and what it's doing now. We've got a pretty good idea that galaxies rotate, but we can't figure that out by sitting and watching it because it would take hundreds of millions of years for it to do one revolution. So we can't simply watch a video of a galaxy to figure out how it's made. But the alternative to watching an individual still or a video of a chess game is, what if we could take a picture of 1 million chess games, all at different stages of the game? If we look at lots of snapshots of chess games, or maybe 1 billion different chess games, then it's a tricky problem, but perhaps with that amount of information we could figure out what the rules of the game are. And that, in a sense, is what we're doing with the universe. We can't simply look at one galaxy and figure out what's going on, but with enough telescopes and enough deep images like this, we can get an idea of, right, there's lots of different types of galaxies, they're all at different distances. We can look, because of the speed of light, we can look back in time and we can get an idea of what galaxies look like now and what they used to look like billions of years ago. And we can see they have different structures and sometimes different colours. Some galaxies appear to be disk-like and look a little bit blue, and others look a little bit more like amorphous blobs and appear to be a bit reddish in colour. The more individual samples we take, the better the picture we get of the whole of the universe. When we look locally, we might think, well, how on earth are we supposed to work out how the universe ended up looking the way it does, when little local bits of the universe look as complicated as this? Perhaps you recognise that we've got a little bit of Orion here, the Orion Nebula over on the right and the Horsehead Nebula down on the bottom left there. It looks extremely complex. Surely the rules of the game that tell us how to make a universe must be incredibly complicated in order to produce anything that looks as complex as that. Well, again, let me draw you to an analogy. Here's a mathematical collection of pixels, a whole load of pixels, each of which has been coloured according to a particular mathematical formula. It's called part of the Mandelbrot set, and we don't need to worry about that, but let's just zoom in to one tiny part of the Mandelbrot set. Strictly speaking, the Mandelbrot set is infinitely complex, in the sense that if we pick any particular part of it and start to zoom in, the more detail we look at, the more detail we see. It isn't simply a collection of pixels which happens to be 1,000 pixels wide or 1,000,000 pixels wide or 1,000,000,000 pixels wide. It's as detailed as we wish to calculate. Using a mathematical formula, we can calculate what the colour of any given pixel is. And we zoom in and we see more and more detail. And just like nature is not repetitive, when we look in closer and closer detail, we see some features, some motifs that look like, well, they look similar to each other, but they're not actually repeating. Some of these little things that look like a seahorse head or something like that, we zoom in and we might see something that again looks a little bit like a seahorse head, but they never actually repeat. The further in we zoom, the more detail we see, and there is essentially no limit to how far we can zoom in, other than the calculation power of the computer that's calculating these pixels. But the point is, what are the rules of the game? How complex must the mathematics be in order to be able to generate billions upon billions upon billions of pixels, of which we're only looking at a tiny number here? We've zoomed in by a factor of maybe a billion. So in other words, compared to the original image we were looking at, we're now looking at a part of the image which is now, something like the size of the Earth or something. How complex must the rules of the game be to generate a really, really complex pattern? Well, the answer is simple. That is the mathematical formula that generated each and every pixel in the entire Mandelbrot set. Z equals Z squared plus C. I'm not going to go through how it generates it, but that's the only bit of mathematics you need in order to generate the Mandelbrot set. So if you can generate something that appears to be infinitely complex with a very simple formula, well, maybe the universe is like that. It looks extremely complicated when we look out there and look at it in detail, but maybe the underlying rules of the game, the laws of physics, are perhaps not that complicated. Complexity is not the same as incomprehensibility. One of my favourite quotes from Einstein is, "The most incomprehensible thing about the world is that it is comprehensible." There is no particular reason why we should be able to figure out what the universe is and where it came from. And yet, the laws of physics appear to let us get a handle on where the universe came from and how it's evolved and why it ends up looking the way it does. Complexity, yes. Incomprehensibility, no. The rules of the game are there for us to discover. So let's just think about the flow of thought. We look out there, what do we see? We see lots of galaxies, which are made of stars and gas and dust and other things. And those galaxies, if we look far enough away, appear to be moving away from each other. So we draw the conclusion that the universe is expanding. Separately, we can do experiments here on Earth. We can make observations of, for instance, what happens if I take a fundamental particle, what happens if I rip an atom apart and look at the particles that it's made of, what if I bang those particles together in a particle accelerator such as the Large Hadron Collider, the LHC. I can do particle physics experiments to get an idea of what the world is made of. And if I know what we are made of and what the Earth is made of, presumably that's the same as the Moon and the Sun and the rest of the universe. There's no reason to expect that the particles we see here on Earth are any different to the particles that we see anywhere else in the universe. And here we do have to make some assumptions to make any progress at all. We have to assume that if we are going to discover what the rules of the game are, the laws of physics, we're going to assume that the laws of physics here are the same as the laws of physics there. In other words, if I can figure out what the laws of physics are, they're the same for me as they are for you. And they're the same for Alpha Centauri. And they're the same for the Andromeda Galaxy. And they are the same for a galaxy sitting at the other edge of the observable universe, tens of billions of light years away. The other assumption we have to make is that the laws of physics now are the same as the laws of physics then. In other words, if I can figure out what the laws of physics are, there's no point in assuming they might change. If the laws of physics tomorrow are going to be different from the laws of physics today, I can't make any progress whatsoever in understanding the world if the rules keep changing. If somebody keeps moving the goalposts, you can't make any progress. So it's a fundamental assumption that we have to assume that there are such things as the rules, and we can figure out what they are, and we'll assume that they don't change with time and they don't change with your location within the universe. In other words, the laws of physics are immutable. What conclusion do we come to when we look at the expanding universe and we do some experiments here on Earth about how particles behave, how matter behaves? Well, we come to a conclusion. We come to the conclusion that the universe was born in a very hot, dense state, 13.8 billion years ago, and ever since then it's been expanding and cooling. So it started off very small and very hot, and since then it's been getting bigger and bigger and bigger and getting colder and colder and colder. So the big question is, Where did all the matter that we see today come from? We look out and we see a huge amount of matter. We see stars, we see gas, we see dust. Some of those stars are collected together in galaxies. There appear to be trillions of galaxies, each of which contain trillions of stars. Where did all this matter come from? That's the question we're trying to answer. If we think we've got a handle on the rules of the game, how far back can we go in time before we have to admit we don't really know whether we understand what the rules are? In other words, how far back in time can we go and still believe that physics is giving us a good handle on what's going on? How far before we give up on the laws of physics? The universe is 13.8 billion years old. What about the first 1 billion years of its history? No problem at all. What about the first million years of the universe's existence? Yes, fine. What about the first 1,000 years? Yep, no problem. What about the first year out of the 13.8 billion years? Yep, no problem. What about the first day? What about the first hour? Yep, no problem. What about the first minute? What about the first second? Yeah, that's fine, no problem. What about the first millisecond? What about the first 1,000th of a second after the Big Bang? Do we think we understand what was going on with the laws of physics at that point? Yeah. What about a microsecond after the Big Bang? Yeah. What about a nanosecond? What about 1/1000th of a second after the Big Bang? Do we believe that we've got a good handle on the laws of physics? Yep. What about the first picosecond? Well, that's where we have to raise our hands and say, I'm not actually sure what was going on if we go back any earlier than that. 1 picosecond, 1/1000th of a second, 1/1,000,000th of 1/1,000,000th of a second. Before that, we are on somewhat shaky ground. From that point onwards, everything is reasonably well understood for reasons that I'll come back to in a few slides' time. So that was a rather long-winded introduction to what this talk is about, trying to understand the rules of the game, i.e. the laws of physics that say how did the universe come to be and how does it end up looking the way it does. We're going to start with a few basic ideas that will then lead into what happened in the first fraction of a second, and then we'll look at the first few seconds, then we'll say what happened in the first few minutes, then we'll change gear slightly, otherwise this talk will take a few million years. We'll then switch to saying what happened in the next 377,000 years. There's a very good reason why we've picked that number. That's not just a random choice. Something in particular happened 377,000 years after the Big Bang. And then again, we'll shift gear again and zoom through the next 13.8 billion years, very much in brief. Okay, so let's get the few basic ideas sorted. Some of this you probably know. For instance, we are made of atoms. I hope that comes as no surprise to many of you. Atoms are essentially a positively charged nucleus with a lot of negatively charged electrons buzzing around them like bees in a beehive. So atoms can be broken down into a nucleus and a whole load of electrons. It takes a certain amount of energy to take an atom and to strip all the electrons off so that we've got separate nucleus and separate electrons. Electrons, as far as we know, are fundamental particles. You can't take an electron and cut it in half and end up with two of something else. An electron is a fundamental particle that is indivisible. A nucleus, on the other hand, is made of other stuff. A nucleus is made of, for instance, protons and neutrons. I'm not going to talk about anything else which might be going on inside the nucleus of an atom. Let's just consider that a nucleus is just made of two constituent parts, protons and neutrons. And again, it takes energy to take a nucleus and to rip the nucleus apart to separate out the protons and the neutrons. And both protons and neutrons, neither of those are fundamental particles in the sense that they are made of smaller building blocks. We could take a proton and we find it's actually made of 3 constituent parts. We don't have to understand the particle physics. Those constituent parts are called quarks, but it doesn't really matter. That's just a name, it's just a label we give to the constituent parts of a proton. Actually, neutrons are also made of quarks as well, but I'm just doing this as a point of illustration to point out that the universe is made, as far as we're concerned, like a Russian doll. The universe appears to be made of stuff which is made of atoms. Atoms are made of smaller things like a nucleus and electrons. Nucleus is made of smaller things. Protons are made of smaller things. And if we wanted to go from atoms to nuclei to protons to quarks, it takes more and more energy to take that particular object and rip it apart to reveal its internal structure. In other words, there's a sort of energy ladder here. The more energy we put in, the more we can rip this stuff apart. As far as a physicist is concerned, low energy and high energy are essentially the same thing as low temperature and high temperature. In other words, if you take a collection of, it doesn't matter what the particles are, if you give it an awful lot of energy, effectively you've raised the temperature of that system. Or if you take a very hot lump or ball of gas, it's got an awful lot of energy, and a cold ball of gas has got rather less energy. So as well as talking about low energy and high energy, we could be talking about cold and hot. And remember, we've already said that as far as we can tell, the universe was born hot and is getting colder. So in other words, time's arrow actually goes from the bottom to the top. So the universe started out at the bottom, hot, and is getting further and further towards the top, cold. And so the universe is being made from the bottom up. We can't expect atoms to exist in the early universe, because the atom would have so much energy when the universe was hot, the atom would be ripped apart. And similarly, a nucleus can't exist in the early universe, because the nucleus would have so much energy because the universe was so hot, the nucleus would be ripped apart. So these structures, protons, nucleus, atom, us eventually, can only exist at particular points of time. Only when the universe is cold enough can quarks make a proton, because before that point the universe was so hot those quarks couldn't stick together to make a proton, because there was so much energy the proton would fly apart. And only at some time later can protons and neutrons make a nucleus as the universe cools. And only sometime later is the universe cold enough for nucleus and electrons to get together and make an atom. Prior to a certain point in time, too much energy exists and the atoms simply couldn't exist. So there is this timeline. This Russian doll is built from the inside out as time goes by, because it's critical how much energy is given to these various particles to determine whether or not quarks can make a proton, whether protons and neutrons can make a nucleus, whether a nucleus can collect some electrons and make an atom. And that's what I'm going to be going through in the next few slides to give us an idea of that progression. The problem is, where do we start? At t equals 0. What happened at the instant of the Big Bang? Well, I've already said that we can go back in time to a very small fraction of a second, up to t equals 0. But strictly speaking, we can't say what happened at t equals 0. We can have ideas, we can have a hypothesis, we can have theories, but we cannot provide evidence, direct evidence, to say what actually happened at t equals 0. It is believed by a number of scientists that perhaps it was a quantum fluctuation. Quantum mechanics is really weird. And quantum mechanics tells us how things behave on very small scales. When we look at the world around us, we can get an idea of what's going on down to the size of, for instance, a cell, a micron or a few millionths of a meter in diameter, and we can understand what's going on quite happily. But if we want to go down to smaller scales, such as nanometers, 1/1000th of a meter, we find that we can only understand that world if we use the mechanics that we call quantum mechanics. Rather than the classical mechanics that we understand from Isaac Newton, we have to involve a different way of looking at the world. And quantum mechanics, this is of course a totally separate thing that I'm not going to talk about in detail, but quantum mechanics does produce a whole load of results which are quite weird and go against common sense. But we know that it is possible for nothing, i.e. the vacuum, to have a fluctuation and suddenly change even though there's apparently nothing there. A quantum fluctuation is a fluctuation in energy, And if we can borrow some energy, then effectively we can borrow some mass. And it's borrowed from nothing, which is, again, completely against common sense, but it appears to be the way the world works on very small scales. You can borrow energy or you can borrow matter from essentially the bank of nothing. You can borrow it as long as you pay back the loan fairly quickly. So how much energy, how much mass could you possibly borrow? How big could the fluctuation be? Well, according to our understanding of quantum mechanics, if we multiply the energy by how long we borrow it for, there is an upper limit. In other words, you can borrow an awful lot of energy as long as you pay it back very quickly, or you can borrow a very small amount of energy for a long time, pretty much like a bank loan. If you borrowed £1 and you were charged interest, you wouldn't be too fussed as to how quickly you paid it back. But if you borrowed £1 million and were being charged interest, you would want to pay that back very quickly. And that's sort of how it works with this idea of a fluctuation. You can borrow energy from nothing as long as you pay it back quickly enough that the universe doesn't notice. That's the basic idea. So the question is, well, okay, if we can borrow a certain amount of energy for a certain length of time, how much are we asking to borrow? Well, the weird thing is, if you work out the total energy of the universe, the total amount of mass, and you can work out its energy from E equals mc squared, and you can work out the energy from all of the gravity, the so-called gravitational energy, which is negative. When you add up all of the negative gravitational energy and add it to all of the positive mass energy, lo and behold, the answer seems to be about 0. So maybe, if we're borrowing 0 energy, maybe we can pay it off. Maybe we've got an indefinite length of time to pay it off. That almost certainly sounds like a cheat. If it doesn't sound like a cheat, you're not paying attention. Yes, it sounds like a cheat, but some people believe that's the way the universe came into existence. Let's jump ahead. And now we're going to jump ahead to a rather short length of time here. You can see the number of zeros along the top there. 10 to the minus 35 seconds, 35 zeros and a 1. At that point, the observable universe that we understand today has expanded from nothing until it's about the size of a golf ball. So I'm saying that that's not necessarily the whole universe. I'm just talking about everything that we can currently see, everything that is currently inside our observable universe, which is something like 100 billion light years across, give or take. Everything that's inside our observable universe now used to be inside a volume about the size of a golf ball. So the universe expanded from nothing to a golf ball in a time period of 10 to the minus 35 seconds. Very rapid expansion. Just like a golf ball, the universe was not perfectly smooth at that point. It had dimples in it. Okay, not little hexagonal dimples like a golf ball, but the analogy is that the universe was not perfectly smooth. Some parts of the universe were slightly more dense than others. Some parts of the universe were a slightly higher temperature than other parts. There were variations in density and variations in temperature. And I'm using the dimples in a golf ball just as a sort of analogy to that. And it's those dimples, those variations in density, such that when the universe has become very, very large, it's those density variations that eventually give rise to matter collapsing and forming stars and galaxies. And we'll see a little simulation of that excuse me, a little bit later. So let's jump now to 1 picosecond. Remember I said that we're going backwards in time, we're fairly good going back to a picosecond. So we're not absolutely sure what happened prior to that. We're not absolutely sure how the universe ended up the size of a golf ball. There are theories, but it's difficult to pin down whether or not they're right or not. Why does it make a difference? Why the watershed at 1 picosecond? The universe, remember, is expanding and cooling. And after about a picosecond, the universe ends up about the size, to give it an idea of scale, about the size of our solar system. Of course, the solar system doesn't exist yet, but just to give you an idea of size. In other words, the universe is not yet the size of, let's say, 1 light year. At 1 picosecond, the temperature has fallen to a mere 10 to the power 15 Kelvin. So what's that? 1,000 million Kelvin. And the reason that we think we've got an idea of what's going on from this point onwards is that the universe, we believe, is just a soup of fundamental particles. Sometimes it's called a quark soup. There'll be a whole load of quarks in there and a whole load of electrons, fundamental particles swimming around in this expanding sphere. And that particular energy, the energy of each of the particles in this soup, is roughly the same as the energy that we can give a proton flying around the Large Hadron Collider. In other words, the amount of energy in this soup is, roughly speaking, the amount of energy that we can reproduce on Earth in a particle accelerator. And hence we can test things with our understanding of banging particles together and see what happens. If we can test our ideas in a particle accelerator, then from this point onwards we've got a reasonably good idea of how the universe evolved. If we can come up with a theory that says this should happen, we can test it because we can reproduce those same energies from this point onwards on Earth. So what's going on? Energy and matter are continually exchanging back and forth. We can imagine borrowing energy from nothing. We can also imagine borrowing matter from nothing. They're continuously back and forth, back and forth. Energy makes matter, matter makes energy, back and forth, back and forth. As well as making matter, energy will make antimatter. So antimatter is simply the opposite of matter. If we think of an electron being a small body with a negative charge, an anti-electron is essentially the same particle, but it has a positive charge. Every particle has as it were, a mirror image with the opposite electric charge. And this is what we call antimatter. And originally, matter and antimatter are made in equal amounts. In other words, if we take a certain amount of energy, I don't know how to represent energy in a PowerPoint presentation other than to give it a large capital E. So if we take a certain amount of energy, that energy can make matter and antimatter. Now, it's probably not going to be a tangerine and an anti-tangerine, but that doesn't matter. It might be a quark and an anti-quark. It might be an electron and an anti-electron. It really doesn't matter. It can generate a particle and an antiparticle, equal amounts of matter and antimatter. And those matter and antimatter can annihilate with each other and produce energy. And that will be happening back and forth and back and forth. That energy can then go on and generate more matter and antimatter. Not necessarily the same quark and anti-quark. It now could generate something different. Probably not a hot dog and an anti-hot dog, but it will generate something and the anti-something. And it will be going backwards and forwards at a very high rate in the early universe. Somehow, through a mechanism we don't really understand as well as we ought to, somehow matter gained a slight excess over antimatter. So in other words, we can imagine, let's imagine that we've got a whole load of matter there, and we've also got a whole load of antimatter, but not quite the same amount. Somehow the energy that was available to the early universe made a certain amount of matter and a slightly different amount of antimatter. Remember, matter and antimatter are going to annihilate with each other, so that tangerine's going to annihilate with its opposite number and produce energy. But what's that little tangerine on the end going to do? Here we have a little bit of matter which can't find any antimatter to annihilate with. So it's just left over as a little bit of matter. The imbalance is not quite as large as I've shown. I've shown that the imbalance is about 10% or so. Actually, the imbalance is not 1 in 10. The imbalance was about 1 part in a billion. So in other words, there's a billion little packets of energy for every little particle of matter that's left over. And the energy is what we call radiation or light, not necessarily visible light, but just generally photons of electromagnetic radiation. And that little bit of matter that's left over because it can't annihilate with anything else, what's that? Well, that's you and me and the Earth and the Sun and the Milky Way and Andromeda and every other galaxy that we see when we look around in the universe. So everything we see in terms of the matter is simply the matter that's left over that couldn't annihilate with any antimatter because they at some point got slightly out of balance. Let's move forward a little further in time. Now we've gone to 1 millisecond, 1,000th of a second after the Big Bang. Matter and antimatter are continuing to pop into and out of existence. And now that the universe has cooled a little bit, it's possible for those quarks to get together. So again, I'm not going to turn this into a lecture on particle physics or nuclear physics. All we need to worry about is that the fundamental particles that were made in the Big Bang, these so-called quarks, can decide to get together, and they happen to like getting together in threes, and a certain combination of three quarks makes a particle that we call a proton. And a slightly different arrangement of those three quarks makes a different particle which we call a neutron. So, in other words, we don't have to worry about why these three particles seem to have different colours, red, green and blue, and we don't have to worry about why some of them are labelled U and some of them are labelled D. It actually stands for up and down, but that doesn't really help our understanding of the situation. All that matters is a certain bag of three quarks is what we call a proton, and a different bag of three quarks is called a neutron. At about 1 second, the universe has cooled to a mere 1 billion Kelvin. So again, we've moved on in time now, and we are 1 second after the Big Bang. So protons and neutrons were quite happy swapping backwards and forwards, because those bag of three quarks, if the three quarks changes, then our label of what's in that bag changes from a proton to a neutron. That's all we need to understand about nuclear physics. And that can happen if there's enough energy. But now that we are at 1 second, the universe has cooled to a mere 1 billion Kelvin, and that's not hot enough for the quarks to readily swap backwards and forwards so that protons can readily swap into neutrons and neutrons can swap into protons. So we're now getting to the point where the universe is too cold for actually protons and neutrons to go backwards and forwards and swap into each other. Now it turns out that protons are a little bit lighter than neutrons by about 0.1%. In other words, we can measure them in the laboratory. And again, there's no reason to assume that the protons that we measure in the lab are any different than the protons in the Sun or the protons in the Andromeda galaxy. Protons are a little bit lighter than neutrons, so although in principle the universe can make a shed load of neutrons and a shed load of protons, if protons are a little bit lighter, then the universe makes more of them. If they were the same mass, the universe would make a 50-50 combination of protons and neutrons. But because the particles are slightly different in weight, the scales on the left tell you that the red-coloured protons are slightly lighter than the blue-coloured neutrons. That means the universe makes more of the protons. Why does the universe make more of the lighter ones? Well, nature always favours a low-energy situation. That one way of thinking of it is, why does a ball roll downhill? Well, a ball rolls downhill because the top of the hill is a high energy situation and the bottom of the hill in the valley, it's a low energy situation, and so the ball will always try and get into the valley, which is the lowest energy situation. That's the way nature works. And if it always favours the lowest energy, that's the same thing as saying it favours the lowest mass, because energy and mass are essentially interchangeable as far as we're concerned here. So because protons are a little bit lighter than neutrons, the universe makes more protons than it does neutrons. And if we've understood the physics correctly, if we've measured the protons and neutrons correctly, we can predict that it ought to make them in the ratio of 75 to 25. So there's a prediction of this particular theory. If we move on to the point of 2 or 3 minutes or so, a little change in the numbers. Neutrons are unstable. We know that because we can measure in the laboratory, we can stick a neutron on its own and watch it, and what it does is it changes into a proton after a little while. So we know that in the early universe, some neutrons will change into protons. So the ratio of protons to neutrons actually changes a little bit after that 75 to 25 that I just showed you. roughly speaking, it changes so that in 16, instead of having the ratio that I showed before, effectively we've now got 14 lots of protons for every 2 lots of neutrons. Just sticking with that same number just for illustration. And now the universe, after 3 minutes or so, has cooled to about 100 million Kelvin. It is possible for protons and neutrons to get together. Remember that timeline? We have to wait till the universe is cold enough to allow this to happen. If we try and put protons and neutrons together to make a nucleus, it'll be too hot and they'll simply fly apart again. But if we wait until about 2 or 3 minutes, the universe is just about cool enough that protons and neutrons can now start to marry up. What sort of structures do protons and neutrons want to make? Well, 2 protons and 2 neutrons is a very stable structure. We know that. We can measure it in the laboratory, and we know that if we take 2 protons and 2 neutrons and put them together, they really like to be together as a family unit, and we call that the nucleus of a helium atom. 2 protons, 2 neutrons. But of course, the number of protons far outweighs the number of neutrons. So in that particular selection of 16 particles that we've chosen there, 2 protons can marry up to 2 neutrons and make a nucleus of helium, but that leaves us with 12 bachelors that have got no neutrons to marry up with. And therefore, what we're left with is 1 nucleus of a helium atom and 12 nuclei of hydrogen, because a proton is simply the nucleus of a hydrogen atom. 2 protons and 2 nucleus is what we call the 2 protons and 2 neutrons, is what we call the nucleus of a helium atom. And now the universe is cold, we can't any longer start generating and swapping between protons and neutrons. That is now frozen into the universe. After 3 minutes, the relative abundance of protons, i.e. the nuclei of hydrogen atoms, and these particles, the 2 protons, 2 neutrons, that we call the nucleus of a helium atom, the relative abundance of those are now fixed. The universe is too cold to start changing protons into neutrons and neutrons into protons. So we can predict that if we've got the physics right, then the universe should be full of that amount of hydrogen and that amount of helium. In terms of mass, let's just count up the circles, count up the blobs, because roughly speaking a proton is a very similar mass to a neutron. So you can see that 1 nucleus of helium has got a mass of 1, 2, 3, 4, and we've got 12 nuclei of hydrogen on the left there. So this predicts that if we look at how much mass of hydrogen and how much mass of helium should be in the universe, the answer should be 3/4 to 1/4, if we've got the physics right. When we actually measure what's out there in the universe and we look at all the hydrogen and all the helium that's out there, what do we find? We find that the mass ratio of those 2 elements are 3/4 to 1/4. That's why we believe we've got the physics right, because the physics predicts a particular ratio of hydrogen to helium, and that is what we actually observe. If our physics was wrong, the universe would make a different proportion of protons and neutrons, and we would end up with a different relative abundance of hydrogen and helium. So that's one of the key reasons why we think we've got the physics right. Now we change a gear and we move forward 377,000 years. So we've gone from 3 minutes to 300,000 years. And that's because nothing really interesting happens for the next third of a million years. The numbers of protons and neutrons is effectively fixed at 3 minutes, and all that happens for the next third of a million years is the universe gets bigger and the universe gets colder. That's pretty much it. However, at some point after 377,000 years, the universe has now expanded to the point where the temperature has dropped to a few thousand Kelvin. Nominally, let's say 3,000 Kelvin. What's so important about that temperature? This now means the universe is cold enough for a nucleus to hang on to its electrons. Before this point, there was so much energy around that a nucleus with an electron buzzing around it, remember a positively charged nucleus, a negatively charged electron, before this point, there was so much energy around the electron would have simply been stripped off the atom. But now the universe is cold enough so that nuclei can actually hang on to their electrons, and so a positively charged nucleus can hang on to negatively charged electrons, and so now, for the first time in the universe's history, atoms can exist. And the universe changes from being an ionized plasma with lots of positive and negative charge everywhere to being this ordered collection of atoms with a positive nucleus and negative electrons. And this is the first time that the universe becomes transparent. A plasma is effectively opaque. A photon of light can't really travel through a plasma without interacting with all of that positive and negative charge. But now we've got electrically neutral atoms, the universe is transparent, and for the first time, photons can go flying through the universe. Light that was up to this point effectively trapped because it was continually being scattered in the plasma is now free to fly across the entire universe. And we see that light today. At the time, the atoms were at, 3,000 Kelvin? They would have been glowing white hot. The amount of electromagnetic radiation they would be producing at that temperature would be visible light. In other words, light with a wavelength of order a micron, a millionth of a meter. We see that light, but we don't see it as a blinding white light in the sky, because now the universe is much larger than it was at 377,000 years. The universe is now something of order 1,000 times bigger than it was when this particular event took place. And so not only is the universe bigger, but the wavelengths that were generated at the time, the light that was generated at the time, has had its wavelength stretched by 1,000-fold. So instead of being 1 micron or so in wavelength, the light is now a millimeter or so in wavelength. So we don't see it as visible light with a wavelength of a micron, we see it as the electromagnetic light that has a wavelength of a millimeter or so, and that's what we call microwaves. That is why we have the cosmic microwave background. It is the light that was released when the universe turned transparent. 1,000 times longer wavelength, the microwaves, than the original visible light of an atom at 3,000 Kelvin. And when we look at the microwaves coming from various parts of the sky, we find that the light is coming from all directions, but there appears to be a little bit of variation. The variation has been exaggerated here for the purpose of this particular all-sky map. Some parts are slightly higher intensity, other are slightly lower intensity. In other words, if we convert that to a temperature, we can say that that part of the sky seems to be a slightly higher temperature than that part of the sky because that's red and that's blue. So why do we get this variation across the sky? Because of the dimples in the golf ball. The universe was not created perfectly uniform. There were density and temperature variations in the golf ball. Once the golf ball has expanded to a much larger sphere, effectively we're looking at those golf ball dimples when we look at the variations in the cosmic microwave background. So that's why people spend a lot of time looking at the microwave background. The variations are effectively a map of the dimples in the golf ball. And hence, the more you study the microwave background, the better understanding you have of what the universe was doing in the very early days, or early fraction of a second, I guess I should say. We can get an idea of what actually happens to the dimples in the golf ball if we do a simulation. If we take a patch, a small cube full of hydrogen, but we allow it to have slightly different density or slightly different temperature in different parts, and we simply let gravity do its stuff. If it was perfectly uniform, nothing interesting would happen. But if we have slight variations in density, and then we simply let gravity do its stuff for the next few billion years, what do we see? We see that the denser parts start collapsing and the density increases. We get a structure which we can liken to filaments and voids, and we get this so-called cosmic web structure, where the individual parts of the golf ball have now collapsed under gravity and produced these filaments, and matter flows along the filaments and starts to collect where the various filaments cross, and that's where matter is collecting. That's where we're starting to form galaxies and clusters of galaxies and superclusters of galaxies in this cosmic web. In other areas, there seems to be very little going on, and we get these voids where we don't seem to see many galaxies, just like we saw in the Sloan Digital Sky Survey 3D atlas that I showed you right at the start of the lecture. Let's just watch that again. From a uniform or almost uniform density, we allow gravity to do its stuff, and we find the denser parts simply collapse on themselves, and you end up with this cosmic web structure. And it's comparing this sort of simulation, the web link at the bottom there, if you'll excuse the pun, takes you to a particular simulation project where you can find many, many more of these simulations of how we go from a relatively uniform structure to the cosmic web, and how that reveals the structure of galaxies and clusters of galaxies. I've got no time in this talk to go through. That's the subject of a completely different talk as to how we end up with particular structures within the galaxies. But if we look at what's going on, for instance, within our neighbourhood, we can see the Milky Way galaxy in the middle there, and this is our local group with the Andromeda galaxy and a few other small satellite galaxies. If we go out in scale and look at what's going on a slightly larger scale, we see the local galactic group in the middle there, but we see the Virgo cluster, a large number of galaxies over on the right there. Down in the bottom left we see the Fornax cluster, and you can start to get the hint of the fact that they are not uniformly spread. We seem to have a sort of filament, if you like, of lots of superclusters of galaxies and other areas which appear to be almost devoid of galaxies. And again, we go out on a slightly larger scale and look at what our neighbours look like. Again, we find that the simulation that we just saw that says we end up with a cosmic web is indeed what we see when we look out at various galaxies in our neighbourhood, not necessarily our immediate neighbourhood, but when we look a few billion light years, we see these structures, and we can see that there are indeed these areas. For instance, there's a region here called the Boötes Void, which appears to have very few galaxies. This is all a result of the dimples in the golf ball collapsing so that we end up with superclusters here, but essentially nothing over there. Let gravity do its stuff. You only need to seed it with very small variations in density in order for gravity to end up producing all of these structures. So on a large scale, the universe looks like a web, or if you like, a foam, depending on exactly what scale you look at it with. If you zoom into certain regions of this foamy structure, you see where the filaments intersect. We get a large density of clusters of galaxies and superclusters and individual galaxies. The more we zoom in, the more we can see familiar clusters of galaxies. Let's just get an idea of what it looks like if we go from the largest scales of billions of parsecs, billions of light years or so. If we zoom into this cosmic foam or cosmic web, we see that the universe looks pretty much the same everywhere, but the more detail we look at, if we zoom into a particular region, we see that the universe is not uniform on a scale of megaparsecs rather than gigaparsecs. We see that if we look on scales of millions of light years, we see individual galaxies, individual clusters and superclusters. And again, this is all the result of various simulations. This particular simulation is called the Millennium Simulation because it was carried out around the turn of the millennium. And again, people are doing these simulations and comparing the simulations to what we see in the sky. Do galaxy clusters actually look like this? Do we get the distributions of masses of galaxies about right? Here we've zoomed into a particular cluster, a particular knot in the filament, and now we're zooming back out again to remind us that that is simply one knot. And on a large scale, if we look at the universe and look in different directions in the universe, and look on a large enough scale, the universe looks essentially uniform, even though in detail we can see individual galaxies being made. What happens in the next 13.8 billion years? Well, once we've got a whole shed load of hydrogen, which the Big Bang provides for us, essentially after 3 minutes or so, now that we've got hydrogen, we have a chance of understanding galaxies and stars and planets, and we can also, to some extent, understand trees and mountains and snowflakes and rainbows and cats and... Okay, perhaps not cats. I don't think anybody will ever understand cats, but on the whole, if we can start with a whole load of hydrogen, then we have a chance of understanding how that hydrogen ends up producing stars and galaxies and other things. A separate talk is more about the detail of how we can go from lots of hydrogen to the galaxies that we see around us. So yes, we have some details of cosmic evolution to work out, but we've got most of what we need at this point. Let's just remind ourselves before we finish in a sort of graphics way. This is a ridiculous timeline with very small times on the left and very long times on the right. There's us after the Big Bang at about 13.8 billion years. And we don't know what happened at zero, but we think a golf ball sized object contained everything that we now see in the observable universe at about 10 to the minus 35 seconds. And that was a sphere that contained basically a soup of fundamental particles. A whole load of quarks plus some electrons as well, because the quarks are positively charged and the electrons would be negatively charged. Eventually, after a fraction of a second, those quarks could get together and the universe would be cold enough that those quarks could form protons and neutrons. And after about 3 minutes, 2 or 3 minutes, those protons and neutrons could get together and form nuclei. Some of them would form helium nuclei and leaving a whole load of protons left over, which is what we now call the hydrogen. And if we wait long enough, after 377,000 years, those nuclei would capture the negatively charged electrons and produce neutral atoms which would allow the light to escape and fly through the universe, because previous to that it was a plasma which is effectively opaque to light. So at that point the universe became transparent and the light eventually became stretched, and that's what we see as microwaves. Nothing much happened for a little while, the so-called Dark Ages, because it takes a little while for stars to start to form. Maybe it took a few million years before stars started to form, and then of course stars started doing their own nuclear fusion business of converting the hydrogen into yet more helium, and so on down the line, creating more and more elements. And eventually we get to the point that we think we understand in terms of lots of stars being made up inside lots of galaxies. So we're not quite all of the way there in terms of our understanding, because the jigsaw is still not complete. We still have a few questions that are outstanding, and they are rather important questions. Why did the matter win over antimatter? Is it, in other words, what caused the asymmetry? Is it simply that some particles that are matter behave differently than some particles that are antimatter? But why do they behave differently? Why is there not a perfect symmetry between the two? We're very grateful that there is an asymmetry, because we are the leftover bits where the matter didn't annihilate with the antimatter. And I've been talking about the observable universe, talking about all the stars, all the gas, all the dust that we can see. But I've not said anything about dark matter. Dark matter appears to exist in addition to ordinary matter, and dark matter seems to be causing the galaxies to rotate at the wrong speed and produce other effects which are a little bit perplexing, because we don't actually know what dark matter is. And we've got even less of an idea of what dark energy is. This is the label we give to the whatever it is that is making the universe not just expand, it's making it accelerate. We might expect that an expanding universe under gravity would slow down and slow down and slow down because gravity is always tugging at all of the bits that are expanding. But in the last few billion years, it would appear to be the opposite. It appears that the universe is accelerating its expansion, and we have no idea what's causing that. So I've called this the beginning of everything, but I've tried to be very careful to talk about everything that we can see in the observable universe. In other words, everything we can see, the stars, the gas, the dust, everything that's in all of the galaxies, trillions of galaxies containing trillions of stars. But all of the ordinary matter that is in stars and gas and dust only accounts for about 4% of the entire universe. The other 96% is still a bit of a mystery, rather embarrassingly to say. But that's another story. Thank you for listening.
Thank you very much, Steve. And could I ask everybody to unmute themselves?